In this video, we'll look at elementary matrices. An elementary matrix represents an elementary row operation. Let's try the following example. Let's find the 3 by 3 elementary matrix that represents the row operation, swap row 1 and row 3. The question we have to ask ourselves is, how is the identity matrix changing? And when we say the identity matrix here, we have to be careful about the size. We're talking about 3 by 3 matrices in this problem. So the identity matrix that we should be visualizing should be a 3 by 3 matrix. It's got ones along the diagonal, and it's got zeros everywhere else. So it helps to have this picture of I in your head as we go through this problem here. Well, if row 1 and row 3 of the identity matrix were swapped, we would end up with this matrix here. 0, 0, 1 would come up to the top, middle row would stay the same, and the bottom row would become 1, 0, 0. So that is the elementary matrix that represents this row operation. Part B. Let's look at the operation replace row 2 with row 2 minus 4 row 3. So again, we look back at the identity matrix and we write down what would happen if we performed this operation on the identity matrix. Well, top and bottom rows would not change, but the middle row, row 2, is going to get replaced with row 2 minus 4 row 3. So that's going to look like this. And for part C, elementary row operation that we'd like to do is take row 1 and divide it through by 8. The elementary matrix that would do that would look like this. So we've just performed the operation row 1 divided by 8 on the identity matrix. Now let's give these elementary matrices some names so that we can talk about them in a little bit more detail. Let's say this one is E1, this one's E2. Let's call this guy E3. So we'd like to figure out what E1 inverse looks like. Well, there's a conceptual way of thinking about this. The idea is that E1 inverse undoes whatever operation that E1 does. So if E1 swaps rows 1 and row 3, E1 inverse is going to undo that operation. It should swap rows 1 and row 3 back again. So this is the operation that we want to encode. The way it's going to get encoded is like this. So there we go. That is E1 inverse. It undoes the operation that E1 performs. Let's try E2 inverse. E2 inverse should undo the operation that E2 does. So to undo this operation here, we're going to have to replace row 2 with row 2 plus 4 row 3. That's going to undo that operation. And what that's going to look like, we can refer back to the identity matrix here and perform this operation on the identity matrix. It's going to look like this. So there we go. We found E2 inverse by thinking about it conceptually rather than actually doing the inverse calculation. Finally, if we wanted to do E3 inverse, we need to undo the operation that E3 did. Instead of dividing row 1 by 8, we'll multiply row 1 by 8. And again, we should refer back to the identity matrix and then say, well, what's it going to look like if we multiply row 1 through by 8? We'll have this matrix here. So there we go. That's the basics of elementary matrices and the fast way for finding the inverse of elementary matrices. Now let's write the matrix A as well as the matrix A inverse as a product of elementary matrices. The idea would be to start with the matrix A and to turn it into the identity matrix using our usual Gauss-Jordan elimination. So let's first swap these two rows. That creates a 1 in the upper left-hand corner. And fortunately, that first column is all done now because we've already got a 0 in the bottom left. So from our current 1, we're going to move down into the right, and this 6 is going to become our new pivot. We'd like to make that a 1. So let's take row 2 divided by 6. Oh, and top row is going to stay the same. So we got 1, 1, 0, 1 at this point. And then very last thing we need to do is clean up that second column. So if we replace row 1 with row 1 minus our pivot row, then there we go, we've got the identity matrix now. All right, so if we represent symbolically what just happened, we started with the matrix A. We performed one operation, then a second, and then a third operation on that matrix, and we created the identity matrix. It's important here to remember that these elementary matrices, they act on the left of the matrix. So you've got E1 to the left of A, that comes in and acts on A. Then we've got E2 acting on that, and then we've got E3 acting on that. So that's the correct way to write things out here. If we look at just this part of the expression here, thinking of this as one object, this is an object that comes in and multiplies with A to give us the identity matrix. So this stuff right here must be A inverse. So we can say A inverse is E3, E2, E1, and it would be nice to write this out explicitly, just writing down exactly what these elementary matrices look like. So on the far right here, we've got E1. That was the first operation that we performed. We swapped rows 1 and row 2. So the elementary matrix that does that is this matrix right here. Second operation that we did, we took row 2 and divided by 6. So that's our elementary matrix for that operation. And the last thing we did was we replaced row 1 with row 1 minus row 2. So the matrix that does that is this matrix here. So the only thing that might be kind of strange with this is just remembering the order, remembering that E1 acts on the left of A. So you've actually got E1 written on the far right side here, and then we're working from right to left. All right, so that's half the problem done right there. We still need to write the matrix A as a product of elementary matrices. So the trick would be to notice that A is A inverse inverse, meaning it is the inverse of this product E3, E2, E1. And we have to remember that when we take the inverse of a product, we're not only getting the inverse of the individual matrices, but the order is reversing. So we're getting E1 inverse, E2 inverse, E3 inverse. And with that, we should be able to write down our answer. All right, so let's look at E1 inverse. It's best to think conceptually here and just think that E1 inverse is going to undo whatever E1 did. Remember, E1 refers to our first operation here. So if E1 represented swapping those rows, E1 inverse is just going to swap them back again, meaning E1 inverse is going to look exactly the same as E1. E2, the second operation that we did, that was dividing row 2 by 6. The inverse of that will be multiplying row 2 by 6. So we picture our identity matrix in our head and we think about what happens if we multiply that second row through by 6. We'd get something that looks like this. If you want, you can have the identity matrix, the 2 by 2 identity matrix drawn out on the side here, just to help picture that row operation. All right, E3 inverse is going to undo whatever E3 did. So we're going to undo this operation here now. Instead of replacing row 1 with row 1 minus row 2, we're going to replace it with row 1 plus row 2. So we're going to get this matrix right here. And there we go, we've written our two matrices as a product of elementary matrices.